We present a comprehensive neural network to model the deformation of human soft tissues including muscle, tendon, fat, and skin. Our approach provides kinematic and active correctives to linear blend skinning that enhance the realism of soft tissue deformation at modest computational cost. Our network accounts for deformations induced by changes in the underlying skeletal joint state as well as the active contractile state of relevant muscles. We generate training data for the neural networks from physics-based simulation of hyperelastic soft tissues in close contact at quasistatic equilibrium. The simulation consists of 3 ordered layers. The deformation of muscles is computed first, followed by an inner skin layer, and lastly a fat layer between the inner skin and outer skin. We model the muscles as isotropic hyperelastic material with anisotropic rest states based on muscle fiber fields. We can obtain a per-element muscle fiber field by solving the Laplace equation with different Dirichlet conditions on muscle origin and insertions. We can generate muscle fiber streamlines flowing from origin to insertions in the fiber field. We model muscle contraction as shrinking the element rest state in the fiber direction and expanding in the orthogonal directions. The finite element muscle simulation finds the solution that minimizes the nonlinear hyperelastic potential energy contributed by muscles, connective tissues membrane, and collision penalty. Next, we constrain most of the vertices on the inner skin layer with barycentric weights and run a linear cloth simulation under tension while colliding with the muscle boundary. Finally, we solve for the equilibrium state of a thin fat volumetric mesh deformed by the constrained inner skin surface. With the simulation results on the muscle and skin, we train the PNN and ANN model to learn per vertex displacements which are added to the rest positions of the mesh. Linear blend skinning will then skin vertex displacements to the desired pose so that the network does not have to learn the transform. In order to reduce dimensionality, we use a PCA final layer so that the network output is simply tens of PCA coefficients. We train both PNN and ANN on muscles as well as the combination of inner and outer skin. The PNN on muscles will produce updated muscle fiber streamlines at given poses. Combining both the inner and outer skin allows us to control the body fat percentage dynamically. It is essential to determine the correct muscle activations required to hold the body in a given pose. Under a quasistatic assumption, we solve for the exact muscle activations which generate forces to the bones that can perfectly cancel out the effects of gravity and other external forces. We determine the unique set of activations such that minimal effort is used to maintain the pose. This forms a KKT system. In this paper, we propose to solve for activations on all muscle fiber streamlines and to use the average of streamline activations to activate muscles. We show some results on our trained PNN and ANN. We first show that PNN fits well on the training data and can generalize to testing data. Next, we present results from our PNN and ANN combined. We compare them with linear blend skinning. Our model shows bulging bicep, trapezius, and deltoid. Here's the effect of increased weights held in the hands. Notice the difference in the level of bicep contraction. We can adjust the body fat percentage by dialing between the inner and outer skin. Now we show streamline activations across different sets of motions. The active streamlines are shown in red, and inactive streamlines are shown in blue. We compare activations with the current state-of-the-art biomechanics model and experiment electromyography data. For tasks of shoulder flexion and abduction, our model is able to capture the observed electromyography patterns on the trapezius, deltoid, and bicep. Here are some more streamline activations on shoulder shrug, flexion, and abduction. Lastly, we show that our model runs more than 1,000 times faster than the simulation. Thank you.